Assalamualaikum. We have covered BJT NPN in the previous video, and we touched about DC analysis and AC analysis. So now let's have a look at an example. This amplifier here consists of a BJT, and this BJT is biased through this resistive network consisting of R1 and R2, RC and RE, VCC and ground. Okay. We know from our previous lecture that if we want to find voltage gain, what we need to find is actually IE here. Alright? We want to find the current IE here. So let's first draw the DC equivalent circuit. So now we have the DC equivalent circuit without the capacitances. So our goal here is to find IE, and in order to find IE, okay, we need to simplify this section. There's actually two ways of doing this. One is to use the voltage divider technique, and the other technique is to use Thevenin equivalent circuit. The voltage divider technique is considered as the approximate method, and the Thevenin equivalent circuit is the exact method. For voltage divider technique, what we are using is that what we are assuming is that R1 and R2 is acting as though they are in series. They are not in series because at this point where they are connected, there is this base terminal here. Okay, and series is supposed to be just two components being connected. But we can use voltage divider technique if we say that at this point, what this node sees at this point is so high a resistance that current does not want to pass there. What current wants to do is that current all wants to travel from R1 to R2 to ground. And when all the current flows the same, if it's the same current between R1 and R2, it is as though that we are saying R1 is in series with R2. Therefore, we can do voltage divider rule. You are trying to find the voltage at this point in the middle here, which is VB, which is the voltage at the base terminal. So this is the voltage divider technique. So once you know VB, and we already know that VBE here is 0.7, and if we know the value of RE, if we want to find IE, I can easily do a Kirchhoff voltage law in here, and I can get, and VB is what we get from here, from the voltage divider rule. VBE is 0.7 volts, and RE is given in the question, so I can find IE. Why do I want to find IE? Because I know that if I want to find the voltage gain, I need to find IE to get into the small signal model, so that I can find the small signal RE, which is, if you still remember, we covered RE is equals to 26 millivolts over IE. And then I can draw the small signal model. If I use the exact method here, what I need to do is that I need to find Thevenin equivalent circuit seen from these two terminals into here. And when you find that Thevenin equivalent circuit, it will look like this. You have R Thevenin, and then you have V Thevenin, and you still have RE, RC, and this is plus VCC. How do we find the Thevenin equivalent circuit? V Thevenin obtained from V open circuit seen at this terminal. V open circuit seen at this terminal. And to find V open circuit, again, it is actually voltage divider rule. Okay, where you find V open circuit is the same as R2 over R1 plus R2 times VCC. For R Thevenin, R equivalent, when you ground all DC voltage source, and you are seeing it from, again, this terminal as well. R Thevenin is equals to R equivalent, and in this case it is actually, if you ground this top part, this part here is actually ground, so that is effectively having R1 parallel with R2. Now when you find the R Thevenin and V Thevenin value, this is how the circuit will look like. And don't forget, your purpose in doing this is to find IE. And in order to find IE, you need to do a KVL here, negative V Thevenin plus IB R Thevenin plus base emitter voltage, which is 0.7, plus IE RE equals to 0. What you don't know is IB and IE. When you have two unknowns in a single equation, it means that you need another equations. Two unknowns means you need two equations. So your second equation is making use of the transistor saturation equation. IE is equals to beta plus 1 IB. This problem to find what IE should be. Then once I find out what IE should be, then I'm ready to go on to the AC analysis, where RE small signal is 26 millivolts over IE. And so the question is, how do we know whether we should apply voltage divider technique or use the Thevenin equivalent circuit? So there is a criteria that you should check, because if we want to use voltage divider technique, the concept is that when you look at the resistance as seen from the base terminal to the transistor and to the emitter, it has to be big enough. So the criteria to check is beta RE and 10R2. If beta RE is greater or equal than 10R2, you can use the voltage divider technique. If it is smaller, then you have to use the Thevenin equivalent circuit. As you can see, the voltage divider technique is shorter and simpler compared to the Thevenin equivalent circuit. But having said that, even if you have to find the Thevenin equivalent circuit, it's not going to be a problem. This is an example where the values of R1, R2, RC and RE are replaced with values 33 kilo ohm, 15 kilo ohms, 2 kilo ohms and 820 ohms, powered by 20 volts. Beta is given to be 150 and output resistance is assumed to be infinity. I draw this equivalent circuit and I get the circuit on the right. Okay, I want to check whether it would be eligible for approximate method. So checking here, beta RE is 150 times 820, I get 123 kilo ohm, and 10R2 is 100 kilo ohms. So that means beta RE is less than 10R2. I should not be using voltage divider bias, voltage divider rule if I want to be exact. So I'm going to use exact method. I need to find the Thevenin equivalent circuit. Thevenin equivalent circuit says find open circuit voltage. That's what I do. I find the open circuit voltage. I'm going to scroll up. Open circuit voltage at these two blue dots here. Okay, two blue dots here, so that I can find this V open circuit voltage. Okay, and then I find it to be 6.25 volts, and then I find R Thevenin, which is the equivalent resistance between R1 and R2. Then with this Thevenin equivalent circuit, I have replaced R1 and R2. Between these 2 points here, I've replaced it with a Thevenin equivalent circuit, and I do a KVL, because when I do a KVL here, I get negative V Thevenin plus IB times R Thevenin plus VBE plus IE RE. So from that equation, I also need to use transistor equation, which is IE is equals to beta plus 1 IB. So beta plus 1 is 151, and from here I get my values. IB is 41.38 microamps and IE is 6.25 milliamps. Now if your values are correct, most probably you are right, because I'm usually not very careful with my calculator, but if you find a mistake there, please tell me. The small signal RE is 26 millivolts divided by 6.25 milliamps, so I get it to be 4.16 ohm. Now when I do my AC analysis, R1 and R2 is parallel. BJT is replaced by beta RE and beta IB. R out is infinity, so it's not here. I have RC connected from collector to ground, because VCC has now become AC ground, and emitter because the resistance is bypassed by the capacitor CE, so emitter goes to ground. So finding an expression for AV is V out over V in, where V out is negative beta IB RC. So the current that goes into RC enters V out in the negative terminal here. Ohm's law says it's only positive terminal, so it becomes negative beta IB times RC, and V in here is to find V in. This is actually V in, right? So because all of these are parallel, this, and this are all parallel, but what I want is an expression that contains IB, because my intention is to cancel the IB in the numerator and the denominator. So I find here beta RE times IB, and I get this expression RC over RE, and RC is 2 kilo ohm and RE is 4.16 ohm. So I get my answer to be for the voltage gains to be negative 480.8, and this negative value here indicates that output voltage and the input voltage is out of phase. So for comparison, I have copied the same example, but I have changed the value of R2 to be changed from 15 kilo ohms to 10 kilo ohms. So now when I do the criteria comparison of beta RE and 10 R2, it is now eligible for VDR. And if I have that, it's the same circuit, yeah, everything else the same, it's just that R2 has changed so that we can do voltage divider rule here, and I get VB to be 4.65 volts. VB, this is VB to ground, so VB is 4.65 volts, and if I do KVL at this loop, okay, I will find IE to be 4.82 milliamp. Take note that I do not need to use IE equals to beta plus 1 IB here, because I already know VB, and I only have to consider VB, VBE, and IERE. The small signal model value RE is now 5.39 ohms. For the AC analysis, the small signal equivalent circuit is still the same as it was with the previous example. The expression for voltage gain is V out over V in. V out is still negative beta IB RC, and V in is still the voltage drop across beta RE, which is IB times beta RE. And the value now has been reduced to negative 370.8. I'm just going to include one more recap from analog 1, which is what happens if there is a source resistance here. This is the same amplifier, but the source resistance is 1 kilo ohm. Okay, so the DC analysis is the same, because this isolation capacitance will keep this voltage source and the 1 kilo ohm away from the DC biasing action to the bipolar junction transistor. So what is different? What is different is the small signal equivalent circuit, and it will affect the AC gain. So when I do my AC analysis, the small signal equivalent circuit now will have to include the source resistance RS, because the capacitance makes it as a short circuit, and therefore there will be a connection to the amplifier. So if I consider AV equals to V out over V in, it's no change. Okay, the expression is still negative RC over small signal RE. But for the whole system, if I consider the gain of the system, then I will have to consider V out over Vs. And for the gain of the system, V out over Vs is going to decrease because Vs is greater than V in. Okay, AV is going to be V out over V in times V in over Vs, and I can find V in over Vs from voltage divider rule, and RS with the R equivalent of all this amplifier can be represented by R equivalent prime, where R equivalent prime is R1 parallel with R2 parallel with beta RE equal to 588.4 ohm. And when I do the voltage divider rule, V in is expressed in the form of V in over Vs because we want to replace it in here. Okay, for the system. So AV, maybe I should be more accurate to say that this AV is AV for the system, and this AV is also AV for the system. Now AV for the system is only negative 178.1 after including the source resistance of 1 kilo ohm. Okay, thank you.